Hello to everyone. In this session, we have to discuss D'Alembert's ratio test theorem. Let summation un be a series of positive terms and limit of un plus 1 by un as n tends to infinity is equal to L. Then, if L less than 1, the series summation un is convergent, and L greater than 1, the series summation un is divergent. Here, D'Alembert's ratio test fails if L is equal to 1. Proof: in the statement, the given limit of un plus 1 by un as n tends to infinity is equal to L. Then, by the definition of limit, we have modulus of un plus 1 by un minus L less than epsilon for all n greater than m. So this implies minus epsilon less than un plus 1 by un minus L less than epsilon for all n greater than m. So next step, add L. So we get L minus epsilon less than un plus 1 by un less than n plus epsilon for all n greater than m. Next, rejecting the m terms, let the series becomes u1 plus u2 plus u3 plus dot dot dot. Next, so that L minus epsilon less than un plus 1 by un less than L plus epsilon for all n. Call this equation number 1. Case 1. When L less than 1, we can choose epsilon greater than 0 sufficiently small such that L plus epsilon less than 1. Next time, let L plus epsilon is equal to R, then R less than 1. Now, from equation 1, we have un plus 1 by un less than R for all n. Now, un is equal to un by un minus 1, un minus 1 by un minus 2, un minus 2 by un minus 3, dot 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 u2 by u1 into u1. Here, un can be written like this. This is less than r r r dot r into u1 less than r dot can be written as r raised to n minus 1 into u1. That is un less than u1 into r raised to n minus 1 for all n. Thus, every term of summation un is less than a constant, that is corresponding term of geometric series summation r raised to n minus 1, which is convergent because the common ratio are less than 1. Hence, by comparison test, summation un is convergent. Case 2. When L greater than 1, we can choose epsilon greater than 0 sufficiently small such that L minus epsilon greater than 1. Let L minus epsilon is equal to R, then R greater than 1. Again, by equation 1, we have un plus 1 by un greater than R for all n. Now, un can be written as un by un minus 1, un minus 1 by un minus 2, un minus 2 by un minus 3 up to u2 by u1 into u1 greater than r into r dot 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 u1. So that is r raised to n minus 1 into u1. So that is un is greater than u1 into r raised to n minus 1 for all n. Thus, every term of summation un after leaving the first term is greater than the corresponding term of the geometric series summation r raised to n minus 1. So which is divergent because the common ratio are greater than 1. Hence, by comparison test, summation un is divergent. Hence, the proof of the theorem. Note, if limit of un plus 1 by un as n tends to infinity is equal to 1, then the D'Alembert ratio test fails. So that is, the series may be convergent or divergent. So for this we have to consider the example summation 1 by n. So here we have limit of un plus 1 by un as n tends to infinity is equal to limit of n by n plus 1 as n tends to infinity, that is equal to, so here at numerator n is there, at denominator take n outside, you get 1 plus 1 by n. After applying the limit we get 1. Again consider the series summation 1 by n square. So we get limit of un plus 1 by un as n tends to infinity is equal to limit of, so here un plus 1 is 1 by n plus 1 whole square and un is 1 by n square. So that is limit of n square by n plus 1 whole square as n tends to infinity. So after simplification we get 1. Here in both the cases we have limit of un plus 1 by un as n tends to infinity is equal to 1. But according to P series, summation 1 by n is divergent, whereas summation 1 by n square is convergent. Hence, the ratio test fails. So, in this session, we have discussed about D'Alembert's ratio test. So, these are the reference books for this session. Thank you, one and all.